Welcome back, folks, and the topic of today's video is going to be a focus on the heat part of internal energy and specifically something called specific heat. Alright, so if we think about the internal energy of any system, we said that that's going to be the total energy of the system, which is going to be the sum of the heat contained by the system and the system's capacity to do work or have work done on it. Alright, so what we want to focus on is going to be the Q term in internal energy here. So we're going to find out that there are experiments we can do where we can make the work term go away and focus on the Q or the heat term here as a means of obtaining a value for internal energy. Alright, so one thing that we have to think about here when we talk about heat is that any substance can be characterized by its ability to either absorb or release heat. So in other words, some substances absorb heat quite readily, other substances don't. Alright? So the capacity to absorb or give off heat is actually given by what we call the specific heat, which is again a property of a particular substance. Now, if we take a look at the units of specific heat, we find that those units are going to be joules per gram degrees Celsius. So that leads us to the actual definition of specific heat. So we say that specific heat is the amount of heat measured in joules required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? So it's the heat that we have to put in order to satisfy that requirement. So as we can see, it's going to vary by substance. So if we look, for example, at specific heats measured again in joules per gram degree Celsius for 3 different substances, specifically liquid water, liquid ethyl alcohol, and solid copper, we see values of 4.184 for water, 2.376 for ethyl alcohol in the liquid state, and finally 0.385 for copper. So what this tells me is that water has to absorb a lot more heat to raise 1 gram of it by 1 degree Celsius than, say, ethyl alcohol would. Water has to absorb almost twice as much heat. And then you've got something like copper here, which is a solid metal, and we find that a copper has to actually absorb very little heat in order to raise its temperature for 1 gram of copper by 1 degree Celsius. So what we want to do next is we want to look and see how we can use specific heat in the context of an equation to determine exactly how much heat can be absorbed or given off by a particular substance. Alright, so let's take a look at a simple example using specific heat. So this is a typical kind of calculation that you might be asked to do. So this is number 4B in your handout. So it's asking us to calculate the quantity of heat in kilojoules associated with a 33.5 degrees Celsius decrease in temperature of a 5.85 kilogram aluminum bar if the specific heat of aluminum is 0.903 joules per gram degree Celsius. Alright? So the first thing that we have to recognize here is that we're going to get a negative heat for this system. And the reason for that is because the heat is flowing out of the aluminum and into the surroundings. So what that tells me is that the internal energy of the aluminum is being decreased. So again, we'd expect to get a negative Q out of this thing. Alright, so the general expression that we're going to use, and we're going to see that it's going to work out units-wise, is that Q, which is our heat, is going to equal to the specific heat of the substance times the mass of the substance times the change in temperature that the substance undergoes. So Q equals C times M times delta T. Alright, so it's just a simple matter of plugging into this equation here if I want to determine what heat we're talking about transferring out of the aluminum. Alright, so first I need the specific heat. That's 0.903 joules per gram degree Celsius. Alright, I'm going to multiply by the mass. Now keep in mind, now the mass, since I have grams down here, has to be in terms of grams. I've got kilograms here, so I need to do a quick conversion here. So I know that 5.85 kilograms, okay, needs to be, let's see, 1 kilogram is 1,000 grams. So we've got to multiply by 1,000 here, so that's going to be 5.85 times 10 to the third grams. All right, so that's the actual mass in grams of the aluminum that I've got. Now again, I'm just trying to match up units that I have here in the specific heat. All right, so let's multiply by that mass in grams. And then finally, the delta T. All right, so in terms of my delta T, I said that I've got a 33.5 degrees Celsius decrease in heat. So I'm going to make my delta T negative here, because again, we're seeing a decrease in temperature. The final temperature is less than the initial temperature. Okay, so I'll put a minus 33.5 here. All right, so let's check out units and make sure that everything works out. If I'm after heat, I should be getting units of joules here. So it looks like grams are going to cancel top and bottom here. Looks like degrees Celsius will cancel top and bottom here. So now when I work this out, I get a Q value of, the calculator tells me, minus 176,965 joules. All right, if we follow our sig figs here, we know this is really going to be good to 3 sig figs here. All right, so now I want to convert this to kilojoules because that's what the problem asks me to do. I know how to do that. I know that in 1 kilojoule of heat, I've got 1,000 joules of heat. Joules cancel, I'm left with kilojoules. I'm going to divide by 1,000, so it looks like it's going to take me to minus 177 kilojoules. All right, so that's the actual amount of heat that's going to be lost by the system as it decreases in temperature by a temperature of 33.5 degrees Celsius. Now, why this is important is going to be the point of what we're going to do in class next time, and that's to introduce a concept called calorimetry. And in calorimetry, what we want to do is to use specific heat as a means of being able to exactly quantitate heat transfer between two substances inside of an insulated container. So that's the basis of calorimetry, and that's what we're going to talk about next time in class. So we'll see you then.